Hello, Algebra 2 class. In this video, I'm going to go over Chapter 6, Section 4, Part 2, Properties of Logarithms. We covered two properties before, product and quotient. Now we're going to look at the power property. Well, remember that the product property was that anytime you had two things in a log that were multiplied together, you can change that to the sum of two logs. So for instance, if I had this example here, where I have log base b a to the fourth power. A to the fourth is the same as a times a times a times a. Okay? So what I'm doing here is taking that product property and applying it to each of these multiplications. I'm going to rewrite this log base b of a times a times a times a as log base b of a plus log base b of a plus log, and so 4 log base b of a's, okay? Because each of these multiplications goes to a plus. Well, I have log base b of a plus log base b of a plus log base b of b plus log base b of a. And that is the same as having something like, let's say, n plus n plus n plus n, which is the same as 4n. Okay, so we can rewrite this as 4 times log base b of a. So this actually shows us how we can use a property called the power property. When you have log base b of a power, you can actually take that power and pull that out and put it in front of the log. Okay, this power up here goes down here. The power property of logarithms. So generally, like in general, without numbers, specific numbers, I have log base b of m to the power of p is equal to p times log base b of m. So here's an example of that. Log base 5 of 25 to the fourth. Log base 5 of 25 to the fourth is the same thing as 4 times log base 5 of 25. Okay, we're asked to evaluate, so what is this as a number? Well, log base 5 of 25, 5 to what power gives me 25 would be 2. Well, and since I pulled that 4 out in front, 4 times 2 is 8. This goes to 8, which makes sense because 5 to what power of 25 to the fourth, okay? Well, 25 to the fourth would be the same as 5 squared to the fourth. 5, the power, or base 5 to the second power to the fourth power, which would be 2 times 4, which would be to the power of 8. You can check this on your graphing calculator. Of course, I won't see the work for this, as always. But problems like this, you can check on your graphing calculator. You have that ability. Log base 5 of 25 raised to the fourth power is 8. So it worked. Okay? Makes sense? Hopefully. Sometimes problems will be so large, numbers will be so large that actually, I don't know, let me see, 25 to the 100, I don't know if this will, yep, overflow. Not able to do on your calculator because your calculator only has so much memory. So a problem like this, log base 3 of 27 to the 100th power would not work on your calculator. But we can use the power property and actually evaluate this probably without a calculator at all, because I can take this 100 and I can bring it down out in front. Okay, the power is out in front times log base 3 of 27. 3 to what power gives you 27? 3 to the second is 9. 3 to the third is 27. So the answer to this is actually 300. Okay, 3 to the 300th power gives me 27 to the 100th power. Okay. An important property, and we kind of touched on this already, but just remember that if you ever have log base b of itself, that's always going to be 1, because log base, let's say 5 of 5, well, 5 to what power is 5? The answer is 1. 5 to the first power is 1. Okay. So also notice, I'm going to erase whatever this is. Do I want to erase that? I'm not sure what's going on here. So I'm going to erase that. Okay. If you ever have log base b of b to the x, so the base here is the same as the base, what's inside here is a base. Well, log base b of b is 1, so you can bring the x down in front and look at log base b of b, which would go to 1, and that would be the same as whatever the exponent is. So log base b is asking b to what power gives me b to the x, and the answer would be x. B to the x gives me b to the x. Okay? This is a little bit more tricky of a thought here, but let me see if I can try to explain this. If you ever have a base, so your first thing is the base, and in the power of that base is a log base of x. Okay? So you have a log in the exponent of a base. Okay? That will actually also go to x. The log and the log will cancel out. The log base will cancel out with the base here, just like these bases cancel out, giving you just the only thing that would be remaining would be the thing that's in the log up here. And how that would work is, if we were to convert base b of log base b of x to logarithmic form, so I'm taking this and I'm going to change this exponential form to logarithmic form, I would rewrite this as log base b of what value is equal to the exponent log base b of x. Log base b of what is equal to log base b of x? Well, the answer would be x. Log base b of x is equal to log base b of x. Okay? So the bases cancel. It's kind of like bases cancel out. Kind of. I mean, that's probably not technically a great math term to use there, but I'm going to use it anyway. And log bases cancel out here, leaving what's here. But it requires this number, obviously, to be the same as this number. There's the base in the log has to be the same as the base in the exponent. I'm not sure what this note was here. I'm just going to erase it. I think that was another class previous year had asked me a question. Okay, so two very important properties of logarithmic identities of how things cancel out. And here's an example. If I have 3 raised to the log base 3 of 4, well, this right here would be a case where I have an exponent with a base and a logarithmic with a base, and they're the same. And they're going to cancel each other out, leaving just what's inside the log. It's important that there's nothing else going on in this part. Like there's no plus up here. There's no times out in front of the log up here. It's just a log base 3 of something. Okay. Here I have log base 5 of 5 squared, and in this case the bases also cancel out. Notice I don't have anything else in the log except for exponent with the base I need to a power. So this goes to 4, this goes to 2. You just add those together to get 6. Hopefully those make sense. Those are one of the more trickier things with logarithms, I think, is that the base of the exponent and the base of a log will cancel out when they're combined correctly. They have to be they have to be used correctly, though. I mean, it's not just like anytime you see them. And here's another one that's very similar to the one I just did. It's log base 2 of 2. Okay? Nothing else is inside this logarithm except for base 2 to an exponent. Well, then these bases are going to cancel out, and you're going to just be left with 5. Here I have base 5 raised to the log base 5. So again, there's nothing else going on with the logarithm here. So base 5 and base 5 cancel out, and I'm just given 3. We get 5 minus 3, which is 2. Hopefully that's making sense. One property of logarithms, which I just kind of touched on, would be if you have log base b of something equal to log base b, same bases as always. So you can set the things inside the logs equal to each other. It's kind of like they cancel each other. They cancel out on both sides. It's not dividing both sides. Do not think of it as dividing because it's not multiplication. But it would be equivalent to having the square root of something on both sides. So you can drop the square roots. What you're really doing if you have the square root of x equals the square root of 4, for instance, well then x is equal to 4. What you're really doing is squaring each side to cancel out the logs. And what you would do in this case is you're going to take the exponent of you're going to take each side to the exponent of base b to cancel it out. And if you didn't follow that, maybe don't worry about it. For now, let's just move on and look at an example of what this might look like. Essentially is if you have a problem like log base 3 of mess equals log base 3 of mess, you can just cancel out those logs. They just go away if it's the same log, and very important, there's nothing outside the logs on either side. If there's something outside one of the logs, you'd have to get it down to just a log base 3 on each side. And then at this point, it's just a quadratic, and we'd have to solve this like we solve quadratics. Okay. However, surprise answer here. One of these solutions is actually not a solution because you can't have negatives inside logs. That's one condition of logs, is you can never take a power, you can never take the base of a log, or sorry, you can never take a base of an exponent and get a negative value out of that. 3 to what power gives you negative will never happen. Okay, there's nothing that you can take a base 3 to give you a negative answer. Negative exponents are reciprocals. They give you small numbers, not negatives. It'll never go to negative. So what happens here is and this is just kind of a trick question, this whole last part of it. Hopefully you get the main idea. Don't get hung up on the trickiness here at the end. 6 times negative 3 plus 1 is a negative 17. Because that is negative there, and I don't even know if it's negative on that side, it doesn't matter, because if this is negative, there's no log base 3. So log base 3 of, there's nothing that you can take it to give you a negative 17 out. You'll get an error. So that was a little bit of a tricky ending to that problem, but hopefully the point of this problem isn't to do with that part, although that's that is actually kind of important that you realize that logs won't have negatives inside them. But the point of this problem was that if you have a log base 3 or log base b on both sides and nothing else, you can cancel out you can just drop the log base 3s. Okay. Whew. There's some problems for you to do. Again, I'll post that, and we are done with chapter 6, section 4. Thank you, and good day.